In today's lesson, we are going to be looking at quadratic relations. So in our previous lesson, we had attempted to look at nonlinear or a nonlinear relationship, whether the data turned out to that or not. The idea is that what we're looking at is not going to be a linear relationship. It's not going to form a straight line or appear to be linear. So the specific type of nonlinear relationship that we're going to look at is what we call a quadratic relation. And we're going to be looking at some of the characteristics of it, some of the key features, and how we can identify it. So some of the definitions. So quadratic relation, a relation whose equation is in the form y equals ax squared plus bx plus c. And this is what we would call standard form. And there are going to be other forms of a quadratic relation that we look at. But for right now, this could be one of the forms. A, B, and C are real numbers, and A does not equal 0. So the key thing that does stand out that makes this a quadratic is going to be this squared. So when we have an equation that has an x squared, that is should be a key indicator of a quadratic relation. Now this quadratic relation, it forms a specific type of shape, and it is a shape that we call a parabola. So a parabola is the graph of a quadratic relation. It is a U shape or a parabolic, and it is symmetrical. Now along with that U shape, I will say that it could also be an N shape, and we'll look at two examples of it. But again, that's the general shape. So it's no longer a straight line, it's going to be more this U or N shape. Some of the key features, so it does have what we call a vertex, and a vertex is the point on the parabola where the curve changes direction. So it could be one of two situations, and we can see it here. So this is what our quadratic relation could look like. It could look like this N shape, where the curve is opening down, or this U shape to the right, where the curve is opening up. So if the point or the vertex is at the top, because it is curving down like here, that is our maximum point. So our vertex could be our maximum point. And if it opens up like on the right, this vertex is our minimum point. So it could be one of two things. It just depends on what type of relation or what type of quadratic relation we're dealing with. Some more definitions. We do have what is called the axis of symmetry, and the axis of symmetry is a line that divides the figure or a figure into two congruent or two equal parts. Right? Basically, it is a line that when I draw it, both sides of the line are going to be symmetrical. Right? So again, we can see that in our two diagrams here, same one as the last page. Our axis of symmetry is this vertical line that cuts our graph into half or two equal parts. Right? And it also, another key feature is that axis of symmetry does go through our vertex. Now, finite differences, we probably looked at finite differences in previous years back in grade 9. Maybe you didn't refer to it as the finite differences. You may know them as first differences, but these are the differences that are found from the y values in tables with evenly spaced x values. And evenly spaced is a key term here. So we do want the x values to be evenly spaced for when we're looking for the difference or the change in the y values. So the finite differences you can also think of as like the change in y values, right? When you're looking at them, and for a linear one, we're going to look at what it should be, and hopefully you kind of remember doing that in grade 9. So looking at the first one, we want to complete the table of values or complete the table for the following linear relation. We want to calculate the y values and then the first differences. So in the first one, it's already been done. X is -2, y is -1. If you're not sure where we got that -1 from, we take the x value and plug it into the equation. So for the next one, it would be y equals 2 times -1 instead of x, plus 3. And in this case, we get -2 plus 3. -2 plus 3, -2 plus 3. We have a y value that's equal to +1. So that means the y value is positive 1. The next one, again, we do the same thing, except instead of negative 1, we would plug in 0. So 2 times 0 plus 3, we get a y value equal to 3. And we could do the same thing for the next one and so on. We would have 5 and we would have 7. So that's just filling out the table, right? I'm just plugging the x values in, right, to calculate the y values. So if you have to put that as a reminder, plug x values in. The next step, right, is to calculate the first differences. And the first differences are basically just what are the y values changing by when x is evenly spaced. So looking at x is evenly spaced. We go -2, -1, 0, 1, 2. They're all increasing by 1, which is good. That's what we want to see. We want to see that increase, that consistent increase by the same amount. The first difference is we're going to do the same thing, except we're going to look at the y values. So -1 to 1, that's a change of 2, or positive 2. From 1 to 3, that is also a change of 2. From 3 to 5, that's 2. And from 5 to 7, that's also 2. So again, you may remember doing this in grade 9. Right? This is one of the ways that we can check to see if a relationship is linear. Because what do we notice about the first differences for a linear relationship? And we should notice the first differences are all the same. They're all the same values, so they're all 2. Looking at the next value, now we're going to be doing the same thing, but for a quadratic relation, and we're going to be doing the first and second differences. So you can probably take a guess at what you think is going to happen when we look at the first and second differences. If you're not quite sure, that's okay. We're going to go through and look at it, but we should think that it probably isn't going to be the same as the linear relationship. So we're going to do the same thing. We're going to plug the x values into our equation and solve for y. So instead of, when we plug -2 in, we get -4. If I plug -1 in, that's -1 squared plus 2 times -1 minus 4. So I would have 1 minus 2 minus 4. I would have -5, or y equals to -5. One thing you want to keep in mind, right, when you square a negative value, remember it should be a positive. So make sure you're putting brackets when you square those negative numbers. Otherwise, calculators may not think the negative is included in the square. If I do the same thing for 0, I get -4. For +1, I get 1 squared plus 2 minus 4. I end up at -1. And for 2, I get 4 plus 4 minus 4. So again, I'm just plugging the values in, or 4. So we're going to go through and look at the first differences. It's going to be the same thing that we did in the last one. Look at what the y values are changing by. The x values, I can already see they're going up by an even amount every time. They're all going up by 1s. Right? So the first difference is I'm looking at the y values. So -4 to -5, that is a change of -1 because we go down 1. From -5 to -4, that is a change of +1. I'm going up 1. From -4 to -1, that is a change of +3. And from -1 to +4, that is a change of +5. I'm going to do the same thing for the second differences, except instead of looking at the y values, I'm going to look at the the first differences. So I'm doing the exact same thing, except I'm looking at the first differences. So -1 to +1, that's an increase of 2. From 1 to 3, that's an increase of 2. From 3 to 5, that's an increase of 2. So looking at this, what is true about the first differences for a, shouldn't be for linear, should be for a quadratic. We already know for a linear what it is. For a linear, it was the same, but for a quadratic, make that a little bit more legible, just so when we look back on these notes, it's a little bit clearer. So if we, what is true about the first differences for a quadratic relation? They are not the same. And what is true about the second differences for a quadratic relationship? Right? And so looking at this, they are the same. And so write a rule for this. So basically just a rule, right? We're not coming up with an equation. We're already given the equation, but for our rule, we can say if the second differences or second diffs are equal, or this will not say equal, let's say the same, it is a quadratic. So again, just that understanding as if I'm given a table of values, I can check to see if it is a quadratic or a linear relationship. Right? We probably already knew, or hopefully we knew the first differences from grade 9. Now we know second differences, which will help us determine whether or not it is a quadratic. Example 3, the arch under the Eiffel Tower can be approximated by the relation y equals 2x squared plus 8, where y is the height in meters above the ground and x is the width in meters from the center of the tower. So we want to come up with a table to graph this quadratic relation. So I'm going to just create a hypothetical table. I have an x and a y. I'm going to choose some nice values. I'm going to choose -4, -2, 0, 2, and 4. That should hopefully give me a good idea of what my relationship looks like. Again, however we choose, whatever values we choose to use is fine, right? I would say you want an equal number on either side of the 0, right? Because we're talking about the center being at 0 and then left and right negative and positive. So similar to the last one, we have our equation up here. We are going to plug our x values into this equation and solve. Right? So for the first one, we'd have y is equal to 2 times -4 squared plus 8. So here we have y is equal to 2 times -4 squared plus 8, or y is equal to 40. I think we have an incorrect equation here. So it should probably be negative, and I'm just doing that because of my prior knowledge of quadratic relations. So it should be a negative. So let's go back and make that change. So -2 times 4 squared, or -4 squared, plus 8 works out to -24. Okay, that I can't graph, right? But let's go through and do the next one. -2. I'm just kind of spacing this out a bit. 0, 2, 4. So if I plug in 2, again, same idea. Y is equal to -2 times -2 squared plus 8. -2 times -2 squared plus 8 gives me 0. So that one I can plot at -2, it is 0. I'm going to plug 0 in, and I'm going to get 8 for a value. I'm going to plug +2 in, and I am going to get the same value of 0. And if I plug in +4, I'm going to get the same thing as -4, which is -24. So going back to that image of a parabola, we should see that we have kind of a symmetrical shape. So that's why I'm kind of automatically assuming what the values are for 2 when x is 2 and x is 4, because I've already done the same values on the other side of the center, or on the other side of that axis of symmetry. So you should see that kind of repetition between of y values. So negative 24, 0, 8, 0, negative 24, right? So you should kind of see that repetition or that repeating of values. So describe the shape of the arch. So what does this arch look like? Well, it does have that N shape. It is a quadratic, so we can call it a parabola. We could say it opens down. How tall and wide is the arch, right? So by looking at this graph of the points, we could say it is 8 it's meters, so 8 meters tall. And how wide is it? Well, if I see where it's touching the ground, right? These 2 points, these x-intercepts, they indicate when it's touching the ground, right? Along the x-axis when the height is 0. So we have a -2 to +2. So it is 4 meters wide. We could say from -2 to +2, right? So that's where we're getting that that width of 4. So again, this is just kind of a quick example of just kind of plugging values into a quadratic relation, graphing them, and just being able to describe the shape, right, and some characteristics of it, right? Because we might have to determine some of these key features or these characteristics of whatever this quadratic is modeling.